Welcome to The Explainer. Today, we're going to decode the secret language of computers. It's a language that somehow runs our entire digital world with just two letters, zeros and ones. So how on earth does that work? But before we even get to computers, let's start with a question you've probably never really thought about. We can imagine any number, right? From 10 to 10 trillion, but we only use these 10 little symbols to write them all down. Why just these 10?
Well, the simplest theory, and honestly it's pretty elegant, is that it comes from the very first counting tool any of us ever had, our own two hands. 10 fingers, 10 symbols. It's just so intuitive that it became the default for pretty much all of humanity.
And this system, the decimal or base 10 system, it is so deeply baked into our brains that it feels like the only way to think about numbers. But it's not.
Not even close. If you actually look around, you'll see these little ghosts of other systems everywhere. Our whole measurement of time, for example, has nothing to do with base 10. It's a leftover from ancient systems, like the Babylonians who used a base 60 system. And why 60? Well, because it's super easy to divide into smaller chunks.
So that kind of begs a question, right? How can any system, whether it has 10 symbols or 60, represent these huge, basically infinite numbers? Well, the secret is this simple but totally brilliant process you learned way back in grade school, probably without ever realizing how powerful it was.
You remember this, right? Place value. The position of a digit completely changes its value. A 7 sitting in the tens column is worth 70, but you slide that exact same 7 one spot over to the hundreds column, and now it's worth 700. Same symbol, totally different value, all based on where it sits.
Okay, let's reimagine this for a second. Let's call it a coupon system. You're not just holding numbers, you're collecting coupons. You've got coupons for ones, coupons for tens, coupons for hundreds, and so on. Any number you can possibly think of is just a particular collection of these coupons.
Now, in our base 10 coupon game, there is one rule that you absolutely cannot break. You cannot hold 10 coupons of the same type. It's just not allowed. The second you get your 10th one coupon, bam, you are forced to trade all 10 of them up for one single, more valuable 10 coupon. This whole trading up system is the engine that makes all of math work.
And here is the really cool part. That trade-up rule, it's completely adaptable. It's the engine that makes any number system run. So if you only had 4 symbols to work with, your trade-up rule would just kick in after 3. And if you stripped it all the way down to the absolute bare minimum, just 2 symbols, you'd have to trade up after just 1.
And that last one, that super simple idea of a system with just 2 symbols and a rule to trade up after 1, well, that is the foundation of the most important number system in the entire modern world.
So, welcome to the binary system. This is the native language of every single computer on the planet. Here, the coupon values aren't ones, tens, and hundreds. Nope. The coupons are for ones, then twos, then fours, eights, 16s. You see the pattern, right? Each place value is just double the one before it.
And with this system, you can represent any number at all. I mean, look at this long, crazy-looking string of ones and zeros. That's just how a computer writes the number 1973. It looks like a total mess to us, but it's just our same old coupon system. It's a collection of one coupon for 1024, plus one for 512, plus one for 256, and so on. And when you add them all up, you get 1973.
Okay, so we can write numbers in binary. Big deal, right? That's great for us humans. But how in the world do we get a machine, which, let's be honest, is basically just a rock that we tricked into thinking, to actually do math with them? And this is where your brain has to do a little flip. Because in the computer's world, 1 plus 1 does not equal 2. It equals 1, 0. And no, that's not the number 10, but it is the key to absolutely everything.
So why? Why does 1 plus 1 equal 1, 0? Just think back to our coupon rule. The binary system has no symbol for the number 2. It doesn't exist. The only symbols you're allowed to use are 0 and 1. So the second you get 2 1 coupons, you've broken the rule. You have to trade up.
Right, and that trade-up has a special name. It's called a carry. You trade your 2 1 coupons for a single 2 coupon. So the result in the ones column becomes 0, and you carry a 1 over to the twos column. 1 plus 1 equals 0, carry the 1. Okay, but this is all still just math on paper, isn't it? How do you get a physical thing, a machine, to understand any of this abstract stuff? The answer, as it turns out, is brilliantly simple. You use electricity.
See, a computer doesn't see numbers. It has no idea what a 1 or a 0 is. All it understands is electrical states. So we make a very simple agreement with it. We say, hey computer, if you see a high voltage signal, let's say 5 volts, just think of that as a 1. And if you see a low voltage, basically nothing, think of that as a 0. Simple as that.
And once you have that basic rule in place, high voltage is 1, low voltage is 0, then engineers can build these tiny little physical circuits called adders. These things are literally hardwired to take voltage levels in as inputs and produce the correct voltage outputs, perfectly mimicking the rules of binary math, including that all-important carry.
So this all leads us to the final and really the most important question. Why? Why go through all this trouble? Why didn't we just build a computer that understands our normal 10-digit system right from the start? And the answer is just about simplicity and reliability. Imagine trying to build a tiny switch that has to reliably click into 10 distinct positions. Now imagine one that just has to be either on or off. Which one is going to be easier to build? Which one is way less likely to make a mistake? The on-off switch, right? Every single time. Well, that's the difference between a base 10 computer and a binary one.
So yeah, while binary code looks incredibly complicated to our base 10 trained brains, we actually chose it for the exact opposite reason. For a machine, it is the simplest, most robust, most stripped-down way possible to represent information. It is literally as simple as a light switch being either on or off.
And you know, this just brilliantly illustrates the true purpose of mathematics. It's not some tool we invented to make simple things complicated. It's a tool for looking at a chaotic, complex universe and finding the simple, elegant rules that are holding it all together.
So think about it. From our 10 fingers, we built a digital universe that runs on trillions of calculations every second. And it's all built on a simple choice between on and off. It leaves you with a pretty fascinating question. If the most complex tool humanity has ever built is based on the simplest possible logic, what are the true limits of what it can achieve?